organized this wonderful school, Marcus, Hilda, Albert, who I suppose is quite relaxing this morning. and, and secondly, I would like to thank you for attending this presentation on Sunday morning. I know that can be difficult after Saturday night in Sao Paulo, so I appreciate your effort. So I will present you our recent works about on brain networks. My group is a research group on epilepsy. We are inside at the Brain Institute of Paris, and we are located inside the Pitié-Salpêtrière Hospital, which is the largest hospital in Europe. It's the place where some famous neurologists were there and worked there. Probably so you know some of them, Charcot and his most famous student, Sigmund Freud, for instance. So we are located inside this hospital, and we are an experimental and theoretical group together with the epilepsy unit of the hospital. So as you can imagine, in the last 30 years, I've been applying tools from complex systems, dynamical systems, nonlinear statistics, in order to study brain dynamics of epileptic patients. And this last part, of course, is mainly done by my PhD students, Martin, who is here, you already know him, and Alice Longena, who unfortunately couldn't come because she's writing her PhD manuscript to defend her PhD thesis very soon. So let's see what can we do with this. So as yesterday, we had some lectures and presentations about the epilepsy. So I suppose that you already are more familiar with this pathology. And it's a neurological disorder generally associated, it's an hypothesis, associated to network alteration. And of course, the epileptic patients, most of them are, during their day, they are normal. Most of the days, they are normal. The brain activity seems normal. It's called, this period, normal activity is called interictal. And on the opposite side, during the seizures, there is a strong and widespread synchronization across all the different some brain areas. And since several years, unfortunately, Klaus is not here. In the 90s, there was a kind of interest for applying nonlinear tools, nonlinear statistics, in order to discover, to detect if there was a pre-seizure or pre-ictal period. As you can imagine, the interest was to prevent the patient of an arrive on seizure. But with the years, there has been some problems, statistical problem. Researchers, we have detected some statistical problems with some methods. And so the topic was abandoned for a while. And since the last, let's say, 5-6 years, the topic, again, has regained an interest, especially because some tools developed, for instance, by the group of Iten, who allows for long-term recordings, so for implanted long-term recordings. So the main hypothesis, as I tell you, is that the epilepsy is associated to a network disease, connection synchronization disease. And it's not very stupid to think that the seizures are, or the origin of seizure and the spreading of seizures are facilitated by an aberrant connectivity, structural, anatomical connectivity. In the pioneering works of seizure anticipation, people used to consider in the following scenario that has been presented also by Klaus. Now, you have the normal activity, the interictal. Some of patients, they display a normal activity, a normal behavior. On the opposite side, the ictal, yes, this one, the seizures. This is the seizure. And as Klaus, and I don't remember who already mentioned it, some patients say that they have auras, but the auras is part of the seizure. Unfortunately, they are part of the seizure. Some of them are olfactive hallucinations, some feelings. Some patients say, oh, a seizure is coming. I feel that a seizure is coming. But the seizures is already there, the seizure. But interesting, before the seizures, not in the second, but sometimes minutes, sometimes hours before the seizure, there are some subjective symptoms called prodromes. Sometimes some patients say, I have a headache. I don't feel well. I mean, all of us, some days when we wake up, we say, I feel strange. Today, it will not be an easy day. So it's a kind of very subjective feeling. So especially, for instance, if you, in my case, my mother language is not French, and some days when I woke up, I said, oh, I'm not able to speak French. I don't know why, but the French will be difficult today. So this kind of subjective symptoms, some patients describe these kinds of prodromes, and some studies have related these prodromes to an activity previous to seizures. And more interesting for the school, of course, there has been different studies. I think one of the pioneering works was that of Klaus and my own group in the 90s, who found that there were some changes on the level of synchrony during the dynamics prior to the seizures. It's not a unique route to the seizure, of course. Some patients here it's only as for the sake of illustration, I indicated there can be a loss of synchrony used before the seizure. The seizure, as you know, is characterized by an increase, a massive synchrony of the different brain areas, but what's happening just before? And the problem here is that there is not a unique pattern that can be observed before seizure. Of course, unique in the sense different from the normal activity, different from the seizures, but also can be different across patients, because there is not only a one type of epilepsy, as the colleague Clarissa and Klaus explained it yesterday. There are a lot of types of epilepsies. So this pattern sometimes cannot be easy to identify. So the classical, when people study brain networks, they use practically a unified framework to analyze the data, and it's the following. You have some recordings from the electrodes, sensors, voxels, your favorite measure. You obtain time series. Each sensor or voxel or brain area is associated to a node. You get the time series, and then you apply your favorite statistic, linear, nonlinear, causality, and so on, to obtain a connectivity matrix. And then people here, up to 10 years ago, people used to work with this matrix. Then with the arrival of graph theory, the complex network theory, people found that we can convert this matrix by applying a threshold, and a statistical threshold, for instance, and then we can transform this object in a graph. In a graph where each node, again, represents a brain area, and each link represents the functional interaction between them. It can be the coherence, the correlation, so on. What's interesting is that you can characterize this graph by different parameters or metrics. All of them will characterize different properties at a local or a global scale. And with these parameters, for instance, some of them, the efficiency, the modularity, the degree, means the number of connections, you can apply your favorite statistical tool, machine learning, in order, for instance, to distinguish two groups, patients against healthy subjects, or two different conditions, resting against, I don't know, memory, so on. So this is the classical framework. But now, in my opinion, there is a small problem with this. Difficulty, not a problem, but difficulty is the following, that now, if you check the last papers in the field, you can find that there are about, we counted, 150 parameters that you can extract from a network, from a graph. So which is the most pertinent feature that you can use in the analysis? So people, of course, for instance, here, you may consider that you have two groups, let's say healthy patients against the patients. You can characterize your network of each patient for by 3 different parameters, and if you are lucky, probably you will distinguish the groups, but which parameter? So, okay, now, of course, with the new machines, you can say, I can compute and estimate 1,000 parameters, but I think it's not I mean, from an engineering point of view, can be interesting, but I don't like it. And especially Klaus pointed very clearly yesterday, is when you talk and when you work daily with clinicians, you must explain them what you are trying to do. And for me, even after 25 years or practically 30 years of working with epileptologists and clinicians, I have not yet succeeded to explain that what is the assortativity of a network, the modularity of a network, the local efficiency compared to the global efficiency. I mean, it's not, for me, it's not interesting even to try to explain them. In opposite, I try to find some methods that they can understand. So the problem, as you could understand it, is how to find the good parameters. But there are other options that instead of characterizing the network by different parameters, you can embed the network or the graph, let's say, in a space, in a Euclidean space, where you can use, of course, all the statistical tools that you are familiar with. Because if I come back, here, you cannot apply, for instance, the average of a group of graphs doesn't exist, it's not defined. The variance of a graph applied directly to this object is not defined. So very simple statistical tools are not defined for graphs. But if you embed the nodes in an Euclidean in a space, endow it with a given metric, it's much easier. And what is interesting is the following: most of the embedding techniques respect one thing, that they keep the similarity or the closeness of the nodes. The similarity, if your embedding technique or function is well done, you can see this in the original graph, you have the red nodes that are close together and the blue nodes. And if the encoding or embedding function is correct, when you project all the nodes in a space, you will respect the similarity in the original graph, you will respect it in the embedding space. So which is the advantage of this? There are several advantages. That one of them is that sometimes, it depends on the embedding techniques, of course, you can encode simultaneously different parameters. I mean, there have been some colleagues that have proved that, again, depending on the encoding function, the geometry of the points in this space, you can estimate a small world parameter, clustering index, and so on. So they respect the properties of the graph. Sometimes you can get it him. But there are, of course, some spaces more interesting, as you can see. Here, in our group in the last years, we have decided to explore the hyperbolic embedding. It's not because it's fancy, of course, hyperbolic sounds sexy, so Euclidean, come on, everybody works on Euclidean space. No, I will show you later the main advantage why I think that is, it's worth working on this space. And the hyperbolic embedding, for those from physics, you are familiar. The gravity theory, are familiar with the deformation of space and time. And there are some very common tools, especially theoretical tools. But let's say a few words about the hyperbolic geometry. You have, for instance, here the hyperboloid. An hyperboloid is what is very fancy in the hyperboloid, that by projection, you can project all the data in this hyperboloid on a disk, let's say unitary disk, Poincare disk, etc. And what is very funny is, of course, the space has a negative curvature, geometry. But what is very funny is that the sum of the interior angle of a triangle defined by 3 points in the space, all of us, we learned that in Euclidean space, the angles of a triangle, the sum is 180, but in hyperbolic space, it's not the case anymore. And for me, quite funny is that the circumference is larger than this. You know, for the Euclidean space, you have the equality, but the hyperbolic is not the case. But of course, the straightest possible path in the Euclidean space is a line, and here in the hyperbolic is a curve. So it's not right anymore. But of course, here all the different hyperbolic space, there is not only a single one, I will talk later. You can endow it, you can associate a metric, and if you associate a metric, you can define distance between points in this space. Distance between points in this space, for instance, here, generally we use it here, this distance. It seems horrible, but it has some interesting properties, theoretical properties. But Mario, even if I have some mathematical notions, I cannot still understand very well. Yep. Sorry, like what's the? Mm-hmm. I try to classify the whole brain networks. I try to embed. If you have a single network, you can identify and to characterize different nodes. But if you have different networks, you can try to cluster or classify the whole network. For instance, all the network from the group of patients and the network from the group of healthy subjects, for instance. Yeah. Exactly. I will, in the next slides, I will show you an example of the two problems. So as I was telling you, probably you say, okay, now I have some notions about what hyperbolic geometry is, but I would like to have an example. So, and all of us, we know, we have seen examples in nature of the hyperbolic geometry. And why are the hyperbolic geometries useful? This plant, for instance, is very I mean, you can see it in Europe during Christmas period with the small red, let's say, fruits. And I hope that most of you know this green salad. And the geometry of the leaves is hyperbolic. Why? Because the only geometry that maximizes the surface in a given volume in order to increase this surface to get more nutrients, get more light. And also, I don't know if this is an animal or a plant, it's a marine in a sea, also has the same properties. The surface is hyperbolic. And now, of course, in art, Martin already showed you last time during the flash talk, this example. There is a very well-known artist, Maurice Escher, who used to apply hyperbolic geometry to represent, for instance, the horses, as Martin said, all the horses in the Euclidean space. Please pay attention that there are red and white horses, and all the horses have the same size. But when you project these points in the hyperbolic space, you obtain this, and even if you observe or you can think that the horses close to the periphery are smaller, if you consider the hyperbolic geometry, all the horses have the same size. And now this is okay, only some examples. More interesting, what can we do with this? And this representation can be useful, for instance, for the representation of a hierarchical database or a tree. If your graph is a tree, for instance, and those people working on genetics, genetic tree, or very complex database represented in a hierarchical way. Why? Why they are interesting, the representation? Imagine that you have a very large tree, and you want to represent it in an Euclidean space. You can embed it, you want to embed it in an Euclidean space. If you want to represent the distance between the root and the very last leaf, you would need a very large distance. So your embedding space should be probably one point here and the other point probably at the infinity. But with hyperbolic geometry, because the logarithmic function that is included in the embedding, you can represent very large distance in a very finite space, in this case, a unitary disk. So this representation, this hyperbolic representation, of course, far more appropriated to represent hierarchical structures. Some colleagues from Barcelona, María Ángeles Serrano, Marian Boguñá, have worked a lot on models, how real networks can be, real models of networks that you can capture a lot of properties directly on this geometrical space. So the main advantage is that the hyperbolic embedding of a graph is a compact representation of complex data, hierarchical, and can model, and you can also develop some models of these networks, for instance, that can be useful for the problem of link prediction. Because, of course, you have associated a distance, you have associated a metric, but there are some few problems that I will mention now. But firstly, the application of how we have applied this stuff to our patients. Generally here, this is a study that has been published several, last 2 years ago. Here we have the population. There were 10 patients continually recorded several days. They are implanted as, with similar electrodes as those shown by Ethan yesterday. They undergo a surgery. They implant some electrodes in the head. And we record the activity record. Of course, the patients stay at hospital, not at home. And they stay at hospital. So we recorded the brain, the electrical activity, 24 hours for up to 3 weeks. So you can imagine we have a bunch of data. So, and here I represented the days, day 1, day 2, day 3, and so on. Some days, patients display seizures. Fortunately, they don't display seizures every day. I mean, but here I represent, for instance, the day they have a seizure is indicated here in red. Okay? So, and we estimate the connectivity matrices of this period. But there is an important difference with previous approach, was mentioned especially by Klaus. Imagine that if you record the EEG during the whole day, your vigilance level change. Of course, the patients go to the toilet, the patient eats, the patient sleep, the patient calls to the telephone, the patient watch TV, and all these fluctuations change your synchrony, change the connectivity of your brain, okay? And of course, it's very difficult try to forecast or to even identify seizures or the state previous to the seizure from this data, because that, independently of the artifacts, that probably there are artifacts of movement, sometimes patients, unfortunately, they put out some, I mean, they've moved or tried to move the electrodes, so the signals are quite noisy. But independently of that, there is some internal change of connectivity because the change of your internal state. I mean, when you are tired, your connectivity change. When you are concentrated, change. And of course, the connectivity patterns are not the same when you watch television, when you sleep, when you eat, when you go to the toilets, and when you call your family. So, yep. Yep. Yes, there has been some, in the pioneering works on seizure anticipation, people try to identify from the fluctuation of this matrix on time, they try to identify this period before seizures. But as I mentioned, it is very difficult because it's subjected to, also is affected by change on the basal, by attention state, your own internal state. So instead, this is the current approach, here we said, think about, probably in Sao Paulo not, but in another country without any changing climate. I mean, you check the meteo forecasting, the weather forecasting, generally you check it in the morning. You don't check the weather forecasting every half hour. You check it in the morning, and if you see that the probability of rain is 90%, probably you will take an umbrella. And that's all. Probably there will not be rain. Probably there will be rain, as here in Sao Paulo, in the morning, then the sun, and then another rain after lunch, and then again a beautiful sun, and then another big rain in the afternoon. But in the morning, you can check it and say, okay, there will be rain, I will take an umbrella. So here we have been inspired by this. I try to build a kind of epileptic forecasting inspired like weather. So instead of recording the whole day that we know this affected artifact and so change, why not to measure the synchrony in a very well-controlled state every morning for the patient? In our case, it was 10 days. The patient are at the hospital, please, okay? 10 days, patients are asked to be in front, sit quiet, don't sleep, close your eyes, and be relaxed for 10 minutes. Every day. And it's from these 10 minutes that we record several matrices. But you can use your favorite statistical tool. And then we try it. This is what we try to do. I mean, if we can identify a statistical pattern from these days, probably we can make a forecast of the day that will be a seizure. In this case, I'm not trying to predict every specific seizure. I'm not interested. Now, of course, it would be better if there was a system able to predict every single seizure. But up to now, I think, first, we don't have the right statistical tools to do it. Second, we don't have the right, device to record proper signals to do it. So let's do the better with what we have. And I think that if I provide the patient a probability, Mr. or Miss, probably there is a probability of having a seizure today, a high probability of seizure today. Probably you will have 2 seizures. Probably you will have 1. Probably you will have 10. But at least you can take your own, decision. Say, okay, I'm not going to take the metro, or I will ask someone to be with me during the journey. Okay? And this is the way we did. So for each patient, we built statistical models, I will come back later, of some observed days. For instance, from the previous days. And then we can build this. With this model, I can try to predict the second. Here, for instance, I took the 6 days. There are networks from days without seizures. There are networks of days with seizures. I can try to obtain some features. And then with the model, I can try to predict what will happen in the next day or the next days. Oh, and for the statistical model, of course, we can use your favorite machine learning algorithm, the 2-class model, SVM, or 1-class model, and so on. Okay? Now I come back to the hyperbolic. As you can imagine, we extract the feature from the hyperbolic embedding space. Mario, practically, how can we transform a graph in an hyperbolic, to project the nodes in hyperbolic? There are different algorithms. Some of them, for instance, the algorithm proposed by the group of Barcelona, there is a stochastic component. It's very interesting if you want to model, it's very interesting because it has some nice properties, theoretical properties, but it's stochastic. And who says stochastic says if I run the algorithm 1 time and I run it 2nd time, there are some changes. And for me, it's not interesting. And for the patient, I suppose that is not interesting anymore. So there are other algorithms. One of them, we use it here. It's called coalitions, proposed by these colleagues from Italy, who is now in China. Muscoloni, no, but the main author of the paper, the last author of the paper. It's in China now, and it works on the following way. Imagine you have a graph, whatever, not only brain network. You can, your ecological or your favorite network. You can associate a weight to the link, or if you have already a weighted network, you can start here. Then you apply your favorite statistical nonlinear dimension reduction. I think in the Monday, Thursday, first days, some people talked about Laplacian, of the projection of Laplacian. I mean, a projection of a graph based on the Laplacian of the associated graph. So you project your nodes here, and then you make a correction. You forget about the distance, and you project all these dots in a circle, respecting, you can see there are all the yellow nodes are here, are grouped here, or the orange and red are here. You respect the order or the nodes on the circle. And finally, you associate a distance from a radius from the center of the circle. And this is very funny because here, the radius can be associated or related to the number of connections. So the node with the largest number of connections, the hub, will be always located in a central point of the disk. In contrast, those nodes with very few connections, the leaves of a tree, will have the tendency to be concentrated in the periphery. And this, the colleagues, Muscoloni and colleagues, have proved that this procedure, all the embedding data, corresponds perfectly to an hyperbolic space. But now, okay, how can we deal with, I mean, statistically work with this data? Let me show you an example. I think with all this week we have heard about phases, especially for the famous Kuramoto model. So, but imagine that you want to do some estimation of a probabilistic distribution. In an Euclidean space, it's very easy. If you have unidimensional data, you can estimate your favorite Gaussian to the data. But for the circular, you cannot apply the Gaussian directly as it is. There is a function associated to a Gaussian distribution on the circle that is called the von Mises distribution that you can see that is quite close to a Gaussian. Here is the center of the distribution. Here is a parameter generally associated to a variance, but here you can see is this function is a horrible thing called the zero-ordered modified Bessel function of the first kind, please, of the first kind. So you can imagine that trying, of course, Python, MATLAB, do that automatically. I mean, if you provide the points around the circle, Python and MATLAB, certainly you will find some tool that you able to draw a kind of Gaussian on the circle. But if you want to do theoretical analysis, try to define, for instance, a machine learning classifier with this, because this kind of expression, it becomes very difficult. So can be fancy, but it's difficult. So but fortunately, there are some tricky aspects that you can project your data. The most classical approach is the following. If you have your circular data, you can project it, for instance, on the tangent. Let's say the tangent located here at the P. So you have now a tangent. You project all the data. And here, you can apply, you can estimate the Gaussian without, let's say, with less effort than on the circle. But not only that, you can also provide some, your favorite machine learning tools, or you can work here. Okay, Mario, why did you transform? And then you lose the interesting part of the hyperbolic embedding. You are losing. Yes, but you can come back. You can come back to the original hyperbolic space. Now, all the different hyperbolic spaces or hyperbolic models have a tangent. You can define a tangent. For instance, for the hyperboloid, here in orange, red, the tangent is this blue plane where you can project. And please believe me, even the disk, if you cannot visualize it, the tangent in a disk, It can be difficult to visualize it, but you can define it mathematically. And this is the definition. You can project a point, given in the complex notation, in the hyperbolic disk. You can project it on a tangent. You can project on a tangent. You do your statistical tool on the tangent, the Euclidean space, and then you come back. You can project back your data or your result to the disk or to the hyperboloid. How? And this is one example. Here you have data of a network projected, a small network, very only for illustration purposes. You have different data here. We have projected them in a tangent. We estimate the Gaussian, and we reproject it back here. And it's very funny, because I like it because it's kind of bananas. So you have the hyperbolic bananas, because I love bananas. And I was very excited to see that the Gaussians in the hyperbolic disk have this shape of bananas. And of course, this, you can imagine, Martin already told you, this part of the work had mainly done as part of the PhD work of Martin. Now, what can we do with all of that? So how can we extract features from our epileptic networks in this space? This is what we did. We can select, for instance, the reference group. Let's take all the networks from the days without seizures. Without seizure, let's say the normal class, classical approach in statistics. You select the normal class. Then you project your network, network 1, network 2, and so on. And then for each node, here I isolated 3 nodes, the green star, the orange circle, and the red diamond, okay? And for instance, for the green star is a node, I estimate the Gaussian associated to the projection over all the networks. And I get this. Then I move to another node, and I can estimate a Gaussian distribution across all the networks. So at the end, what I have is a model of each node during the seizure-free days. I mean, during these days where the patient don't display any seizure. And of course, now, if I have a new network, think about the statistic. You have your reference class, the normal class, you fit a Gaussian, then you get a new data, and you compare it with the Gaussian. This is what is called a t-test or student test. So you compare the distance of the deviation of a new data with your Gaussian. And here is what we did. For all the nodes, we estimate the distance of the node of a new network. If it's the node number 1, I will use this Gaussian. If it's the node number 2, I will use this Gaussian, and so on. At the end, we can obtain what I call it the hyperbolic score disk, only that represent the features that we will use in the following for the forecasting. So quite complicated, but it's trivial. Don't be afraid about this mess. For instance, in this example, I will take all these days, 5 days, networks from 5 days, to estimate my model. So days in red indicate the days with seizures. Days in green indicates the days without seizures. The associated networks from the different days. So I said that my Gaussian model is estimated only from those days without seizures, the green one. I have this. I have all the model, a statistical model for all the nodes. I estimate the features. And now I have a feature. I can use your favorite machine learning. Here, we have applied a simple logistic function, but you can use SVM. But deep learning, probably not, because you need a lot of data. With neural networks, why not? And finally, once you have your statistical model, the points correspond to the features associated. you have a new feature, a new day. What is happening the next day? You estimate the networks. You, of course, extract the features corresponding to the networks using these models. And you can obtain the probability to assess a probability if the network corresponds to a day with seizure or not. Which are the main results here? So, as I mentioned, the key elements is we estimate that the statistical model from the previous days. We define a region here to estimate the features. We use a logistic regression, and we test on the next days. Okay? Somewhere like that. You have your logistic functions, all the points that correspond to the seizures to the days without seizures, and the red one, the days with seizures. Of course, what happens, you can learn your model with only 2 days, with 3 days, with 5 days, and so on. Of course, more you have, better the model is. And here, for instance, if I build my statistical model only with 1 day from each group, I mean 1 day with seizures and 1 day without seizures, you can see that the accuracy of the forecasting is not very good. There are a lot of variability. Curiously, if we learn with 2 days, the variability increased. We don't know why. We don't know why this phenomenon, the accuracy is not very good, but the variability increases. Quite funny. But if you use 3 days, 3 days with seizures, 3 days without seizures, of course you can see that the median is very good and the variability is considerably reduced. But of course, if you, at the end, you use every day, you learn your model with all the previous ones, the performance is much better. Then there was one referee who asked several months, asked us, okay, it can be nice, but have you tried a very idle and very stupid model that considers, for instance, if I have a seizure today, I can say that tomorrow I will have a seizure. And if it's rain today, there is a high probability that it will be rain tomorrow. And that's all. This is a very simple model. So we try to, we quantify it, this model. We call it the anteriority-based model. If today it's sunny, tomorrow I can assume that the probability of being sunny is quite high, except in Sao Paulo. I learned that this week, that this model is not very good for the weather in Sao Paulo. But it's not good also neither for the epilepsy. You can see the variability is reduced, and the accuracy is reduced, and the variability is very large. But what is interesting, this is for the whole group. But the main advantage for this approach is that you can build a specific predictor for each patient. So each row corresponds to each patient. We have 10 patients. It starts from 0, and it finishes on 9. This is in Python. In MATLAB, it starts with 1 and finishes on 10, but OK. In green, I represent the days without seizures. In red, the red with seizures. And here is the probability of the model, the forecasting probability. Okay? You can see that there are some mistakes. For instance, for this one, here I identified correctly. This is slightly larger than 50% of having a seizure. And it's red. It's OK. Here, there is a mistake, because the algorithm detected associated a probability of 60%, when in reality, there was no seizure. False alarm. Oh, this is a problem. The false alarm is a problem because it can create a stress to the patient. If I say to a patient, hey, today you will have a seizure, yep. Great question, excellent question. And the answer is yes. They follow a modification of the medication, because the objective of their stay at the hospital is to identify where the seizure takes the origin. So what we want, not them, is to provoke seizures. I mean, more seizures they have at the hospital, better it's for the clinicians to identify where the problem is. And the medication is modified. But in the paper of Cousin that I mentioned before, we calculated the probability of how, I mean, if we could predict by this modification, it is not the case. So, but it is very important to check in all the papers, especially in seizure forecasting. Yes, if you diminish your medication, the probability of having a seizure increases. That is very important. Okay? So I was telling that we have, as you can see, we have very few false alarm for our cohort. We have only 2 for false alarm, this one and this one. And please pay attention to the patient, to this false alarm. What we can observe in common, this false alarm and this one. Sorry, this one. The false alarm arrive always after 2 consecutive days with seizures. It's curious. So you had a seizure today, you had a seizure the previous day, yeah, it's almost finished. And the system indicates me that I will probably have a seizure, but it's not the case. So it's very curious. Probably what we think is that these false alarms are associated that probably there's some endogenous mechanism, control endogenous mechanism. The system identifies the high risk of seizures, but fortunately, the internal mechanism of control of the brain, of the system, avoids the seizure. But it's, of course, an hypothesis. And you can say here the main results are following from all the 28 days previous to seizure, days with seizure, they say. This percentage were correctly predicted. Interesting, as I mentioned, the false positive arrived only in only 2 patients. So we are relatively happy with this. And now, I'm almost finishing, but I wanted to stress why using hyperbolic geometry. Okay, it's fancy, it's sexy, I'm working on hyperbolic geometry, like gravitational theory. No, there is a practical reason. Of course, I like it, this kind of model of geometry. Here, with Martin and Alice, the other PhD student, we use it only to illustrate. It's a paper submitted by Alice. Here you have a network of the brain, and the sample modularity of the brain is considered 2 hemispheres. So if your embedding algorithm is right, is correct, it would be able to separate the nodes from the left and right hemisphere, indicated here in red and blue. Okay? For the same patients, we have obtained an anatomical connectivity network and functional network. Here is the representation using which is the forced, there's a kind of representation of the graph proposed by one of the classical tools only to project the graph, to visualize the graph. Here, we have used an Euclidean projection based on the Laplacian maps, on the spectral properties of the Laplacian of the associated graph. What is interesting that for the anatomical network, an Euclidean space, an Euclidean embedding perfectly separates the both hemispheres. Of course, the anatomical networks, generally, they have very few links between the 2 hemispheres, so probably it facilitates. But the functional, the network estimated for fMRI, you can see that the Euclidean distance is not able to separate the hemisphere anymore. But the hyperbolic embedding is able to separate it. So the hyperbolic seems to catch some hidden properties and geometry of the network that cannot be captured by the classical Euclidean embeddings. So this is, for me, the best example why to use hyperbolic embeddings instead of Euclidean ones. And now I finish it by saying 2 things, 2 to 3 things, very important. The first one, of course, okay, the method, we think that it can be a good maker for personally seizure forecasting, specific to each patient. Okay. Now, more from a theoretical and physics or mathematical point of view, is that there are other non-Euclidean space Okay, here we have studied hyperbolic, but there are also a spherical, elliptical projection of a graph that probably can provide similar or probably even better results. And even if you want to work on hyperbolic spaces, there are a lot of models. So Lorentz model, Klein model, even the hyperbolic Poincaré disk, there is the version of D-dimensional, so Poincaré's ball, so I cannot imagine what it is, but okay, there's also something, a model called half-space model. And interesting, very interesting, is that you can pass from one model to another one. I mean, you can project on the hyperboloid, and there is a by very sample projection to obtain the disk, and from the disk you can pass to another. And there are, each model has different characteristics, advantage, and inconvenience. For instance, the Klein model, that you can estimate the distance practically by using something very, very close to Euclidean distance. Okay. And then, of course, you can use your favorite machine learning model. And now the problem, well, no, I mean, probably the study, of course, is limited, the number of patients is limited. But also very important for us is that the study has been done with intracranial electrodes that are, of course, the patients are at the hospital. We don't have any idea what can happen at home, probably by using scalp EEG, but we are very, I mean, we have a lot of hope on the device developed, for instance, by E10 that could provide recording with much better quality than the scalp EEG. So, if you are interested, there was supposed to be the names of the authors of this work, but if you are interested in this work, and we have several papers in the last years in hyperbolic geometry, you can check, discuss with Martin, he can provide you the list. And finally, of course, the group of all our colleagues and collaborators, and of course, thank you very much for your attention.
Questions? Yes.